Hello, my name is Bob D. Hilster, and I am your particle model guru. I'm here today to talk about how the particle model can explain gravity. You should have watched, hopefully you have watched two videos. The first one to be of help here would be to watch my video on two gravities. Explains there the fact that G1 gravity is Newtonian gravity and G2 is is a gravity which is responsible for nuclear binding force. The second video, which would be helpful, is a more recent one titled Particle to Particle Interactions, where I describe that particles can pass through some objects and generally have no effect when they do, or as they pass through, they can bounce off, which will uh, cause the object that's passing through to be pushed, or the object will push back on the particle, or the particle as it passes through can get trapped by, that is, to become an orbital. I've covered those in previous videos. So I'm going to use these videos today to explain G1 gravity and G2 gravity specifically. Okay, as a point of history, pushing gravity is not a new idea. Nicholas Faddeus was actually a friend of Isaac Newton and was helping him on one of the publications of Principia. He had an idea like this. Newton even considered it, but didn't put it in Principia. About 50 years later or so another man came along named Georges Lesage, and he did the same thing. He came up with particle model, a pushing type gravity, and it caught on pretty good. Had some problems, survived for a while, and then uh, lacked some interest. There is a book that I actually have it right here. It's a book titled Pushing Gravity, edited by Matthew Edwards. It has multiple authors in it, all looking at pushing gravity from different perspectives. And it covers pros and cons using those perspectives. And it was published in 2002. So there's been some activity on this even more recently. But the interesting part is when you look up Lesage's gravity, which is basically what it's called in Wikipedia, you read this statement. The mechanical explanation never gained widespread acceptance, although it continued to be studied occasionally by physicists until the beginning of the 20th century. Well, that's not right. The 20th century beginning would be the 1900s, and you can see in 2002 we've had more activity anyway. But by that time, it was generally considered to be conclusively discredited. Mainstream has conclusively discredited this theory. I jokingly say that's why I'm using it, because if mainstream considers it wrong, it can't be all bad. Okay, now in one of the previous videos, I often show this picture of the Earth with these force field around it. The force of acceleration is in the direction towards the center of the Earth. And it is also a stream in the particle model is a stream of the G1 particles. They're low intensity. No pattern, meaning there's no frequency, no wavelength, but they're low intensity because gravity, in fact, is a low intensity wave. But in the particle model, these arrows not only show the direction and the force of acceleration on an object towards the Earth, it can be identified or be interpreted as a stream of particles. So this is a picture of the Earth, and I'm putting some numbers here about showing streams of G1 particles. I got a stream coming from the left, 1,000 of them in some small interval of time, and another stream coming from the right, also 1,000 of them. Again, these numbers are fictitious. I just made them up to make the point. So if you follow from the left, you have 1,000 coming in, and these G1 particles will, in fact, pass through. And as they do, they can bounce off and scatter, or they can be trapped by, which means by the time they reach the other side, which is over here, there's not as many of them. And you can see here that there's 10 of them lost. And what you really have in reality is 990 of these G1 particles coming out of the Earth, or if I had done this vertically, pushing up, while there's 1,000 of them pushing down. Now they're still there. You can say, well, there's only 10 pushing down, but they're still there. 990 are still passing through the apple that's above the Earth. The 1,000 are still passing through the apple, but there is a differential of 10, and it's those 10 extra 10 that gives the extra push to the apple towards the center of the Earth. So it's because of this bouncing and scattering, it's because of them being trapped, that this differential occurs, setting up a force field around the Earth. So however many enter, we always assume that the same number enter on either side. And you have the same thing on the left side. There's a differential there, and you can go all around the Earth, all three directions: equator, North Pole, South Pole, any latitude. Have exactly the same thing with the G2 particle. In this case, we're looking at either a nucleon or the G1 particle. Now we're not at the Earth, which is large. This is a particle which is extremely small. G2 is even smaller. And again, it's the same thing, 1,000 coming in on the left. As it passes through the nucleon, it scatters. The particles scatter and get trapped, and there's fewer of them coming out, so that there is a net force on the right towards the center of the nucleon, or towards the center of the G1, causing the particles, causing a net force towards the nucleon. This is in fact, if this is the nucleon, that is in fact the nucleon or nuclear binding force, the G2. It sets up gravity only when the particle can pass through. And then when it passes through, you have to lose some of them before they go out, and you lose them by one of these two interactions: when they bounce off and push and scatter, or when they get trapped. So you have to have open space to go through a nucleon and a G1. You can't. The nucleon in G1 can't be a solid, hard rock, no space type particle. One of the ways that you have open space in a mechanical model is that these particles, the nucleon in G1, are actually made of subatomic particles. Those are atoms below the normal atoms. So, and I've talked about levels before. We have level 1 atoms, which are made of nucleons and G1s. In this case now, since I'm talking about two levels, I would call the nucleon the N1 particle. And you can take the nucleons, the N1s and the G1s, and you can make up any atom you want, including all of the ones on the periodic table. Level 2 atoms are much, much smaller. The nucleon 2 and the G2 are much, much smaller than N1 and G1. They are level 2 atoms where the G2 is orbiting the N2. Yeah, G2 particles are orbitals of the level 2 atom. Don't know much about these atoms. Don't know if there is even multiple versions of these atoms. Is there a periodic table at level 2? That's an open question. But if you're going to have the G2 passing through the N1 and the G1, they have to have open space. The way that's made One of the ways it's made is to have the nucleon and the G1 made of subatomic atoms. So in summary, level 1 atoms are made from the nucleon 1 and G1 particles. The G1, as I've said before, is the electron, photon, and graviton, basically moving at speed c. G1 gravity moves atoms and molecules and larger objects around the universe. Level 2 atoms, the nucleon 2 and G2 particle. G2 is its own. I don't know of any equivalent. I'm not a particle expert in terms of quantum mechanics, all those particles they talk about, but G2 is its own particle. G2 gravity is a level 1 atomic binding force. G2 gravity applies to light, in particular refraction, which I've already talked about. Talked about refraction, have not yet talked about magnetics, electrostatic circuits, and chemistry. G2 is really widely used in helping to explain how the universe works using the particle model. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.